Bismillah ar-Rahman ar-Rahim. So last time we started to talk about fundamental definitions for network security. We talked about the difference between network security and computer security. And we talked about the main pillars of security services, including confidentiality, integrity, non-repudiation, and so on. And we talked about the different standards and different standard bodies. And then we tried to go deeply into the different types of security services and the classification of these security services in terms of some of these services, they are applied on the level of the message, and some of them are applied on the level of the connection. So we talked about connectionless services and connection-oriented services. So to continue that discussion, we also talked about the difference, of course, between security service and security mechanism. And to continue that discussion today, we are going to dive deeply into the different types of these mechanisms. Of course, throughout the course, we'll talk in details about each of these mechanisms. We'll cover most of them in a lot more details. But for now, we need to understand a very high-level idea about these mechanisms, what they are used for, and also what is the interaction or the relationship between these mechanisms and the services, and how can we group these mechanisms together to provide a certain service at a specific level. So, these mechanisms, these mechanisms, they can be categorized in terms of, similar to the fact that we categorize the services in terms of connection-oriented or connectionless. We talked about peer entity authentication, and we talked about connection-oriented authentication. Here we need to also specify the fact that these mechanisms, they are applied at a certain layer or at a certain level in the network stack. Okay, so for example, encipherment. Encipherment is actually the cryptography or the encryption and decryption, right? So this is the basic encryption and decryption, and the idea of encipherment is to transform the data into a specific form that has no correlation to the original message. Okay. So that if you look at the transformed version of the message, you can have no information whatsoever about the original message. That's the main idea. The other requirement of the encipherment is the fact that if you know the key that you have used to transform the message, okay, only by knowing the key you can transform the message back. If you don't know the key, then it's very hard for you to transform the message back to its origin. That's the main idea of encipherment. But of course, as part of the encipherment, we require a reversibility. So if you know the key, you should be able to reverse back the message.
Actually, you must be.
Yes. Unless there is some error in the message itself, then there is like some level at which you can reconstruct the original message. Okay, so the encipherment talks about transforming the message itself. Okay, so the message itself will get transformed into another form of a message that has no correlation whatsoever to the original message. Unlike that, digital signature is not something. It's not transformation of the message itself. It's something to be appended to the message. Okay, so that if this message is altered by any chance, altered whether through error or through like some attacks or anything. Okay, if the message is altered by any means, then this digital signature will alert us that this message has been altered, in which case we can deal with that accordingly, whether we reject the message or we have to do something about it. So also digital signature is used for, since it's a signature, it also tells us what? It tells us the origin. So it identifies the origin. So we can use that for non-repudiation. Bravo. Okay. So this is the digital signature. It's actually a mechanism by which that we can have like a mathematical relationship or a mathematical form of the exact message that tells us whether or not this message has been altered, and it also tells us the origin of this message. Access control is the mechanism by which I have to categorize the access to a specific resource or a specific device. So I have to specify certain level, whether it's an admin privilege or user privilege or guest privilege and so on and so forth. So in general, we're not gonna discuss access control mechanisms in details because that's usually does not actually get into so much networking aspects. Data integrity on its own, it's not a mechanism. Okay, it's actually a service. I have some reservation on specifying data integrity here. It's actually a service more than so. Even the definition, it's a variety of mechanisms. So it's actually like a group of mechanisms that ensures that if the message has been altered, then we get alerted or we get notified, and we can reject this message based on that. And of course, the data signatures is actually the mechanism that we can use to guarantee or to provide the data integrity. Authentication exchange. We talked about authentication as a as a service. Here, authentication exchange talks about the mechanism or the protocol through which we have to exchange the information to facilitate that authentication. Okay, so authentication exchange is actually a mechanism by which, like for example, if I want to authenticate myself to a server, then I have to provide my credentials, right? So definitely, as you can imagine, I cannot just send my password remotely to a remote server exposed, right? So, as part of this authentication exchange, I might have to use encipherment to actually encrypt or to use some kind of mechanism to ensure that the password is not exposed and so on. So we have to use a mechanism to provide authentication service. We talked about traffic padding. Of course, again, traffic padding is used here for what? It's used here for to provide concealment of the information, right? Why? Because if we don't do padding and if we assume that the message, as part of the protocol, the message itself it has fixed length. If the message has fixed length, then the transformed message will have a fixed length because encipherment does not actually transform the length. It actually provides some transformation to the message without changing the length, right? So if the message itself is fixed, then the encrypted message is fixed. And as we said before, that tells the attacker some information for free. So, so to conceal the properties of the message, we very often use traffic padding. And here traffic padding is not for data alignment because we talked about traffic padding as part of network 1, if some of you remember. And this is only for data alignment. It's like if you imagine, you have a delivery of a parcel, مثلا from Amazon, you open the box and you see another box and you see like some foam around it, right? So it's like this foam is just to fill and align the size of the small shipment with the big box. So traffic padding in network was used for data alignment only, not for actually concealing or. But here, traffic padding, we mean like traffic padding for security. So more often than not, this traffic padding is used before encryption. So we usually change the message size, right? So that the attacker finds that all the messages, they have different sizes. So he has no information whatsoever or has no property whatsoever about the encrypted message. So it's used as part of message or data concealment, right? So, for example, traffic padding and encipherment both are used for message concealment or for confidentiality. Also, routing control. We talked briefly about routing control, if you remember last time. Routing control is also used to, again, to hide the path, even the route that the message goes through. So if we imagine that we have a network of nodes, okay, and if Alice always send the message through that route to Bob, okay, that also tells some information to the attacker. So the attacker can wait here and can listen, for example, to this part of the network and always get all the encrypted messages, okay? So instead of doing that, so we send sometimes through another path. So we have to create some maneuvering through like some routing control. So again, that routing control is also part of information concealment or part of confidentiality. واضح كده؟ Notarization.
Just to touch on this example, when the message moves from one router to another router, it's called hops, right? So there are
Here, if the message goes this way, so that's a hop, that's a hop, that's a hop, that's a hop,
so
right?
there are some algorithms that always try to find the least number of hops.
Right.
So
Right.
in those cases, do these algorithms also consider randomization while trying to find?
That's a good question. So when the routing protocol tries to find the shortest path, right? Many routing mechanisms, especially for security, they try to find the shortest number of K paths, right? Not just one, okay? In some cases, actually, حتى we studied for in network one, what if if two routes have the same cost, right? So some routing protocols, they actually use that property, okay? And they actually store both routes, sometimes to provide security, sometimes to provide full tolerance, sometimes to provide load balancing, right? You know the difference between all of these? So, I mean, the routing protocol can in fact store multiple routes for the same IP address or for the same destination, right? Which can be used to provide different services or different techniques, and one of them is routing control. واضح كده؟
Is it safe to say that practically from one source to one destination, there is never just one K path?
No, we cannot say that because there could be only one path, right? There could be only one path. For example, peer-to-peer communication, like two devices. There's no actually any router between them or ad hoc networks. So we cannot make it a general rule. But if we have this luxury, if we have this flexibility, we can use that to provide more security services, right? Notarization is used for what? Notarization is to define a third party, or sometimes we call it arbitrator, sometimes we call it a certificate authority, where, you know, Alice and Bob, okay, they communicate together, they send to each other like some messages, but these messages have to be vetted by a certificate authority or by a notarization, okay? So this certificate authority or the arbitrator or the notarization entity, it actually, every time Alice sends a message, okay, then it has to vet. Sometimes we use certificates for that. That's why we call it certificate authority. In the message itself, we embed the identification of this security. And through that, this notarization vets that this message comes indeed from Alice and not from anyone else. And that's used for a non-repetition. Bravo عليك. Okay, if Bob receives the message again, the notarization or the arbitrator or the certificate authority has to also vet that indeed Bob received the message and no one else. ماشي كده؟ So these mechanisms, as we said, they provide they provide a specific technique or a mechanism which is usually used within a certain layer. Like for example, TLS uses a specific encipherment mechanism, like AAS. We'll study that to provide مثلا confidentiality in the transport layer and so on. So usually these mechanisms are applied on the level of a layer. Unlike that, there are certain mechanisms which have nothing to do with a specific layer. Okay, they don't have anything to do with specific layers. These types of mechanisms were not focused on them so much in this course, naturally, because these are not to be applied. Some of them we will, like the audit trail or event detection, especially when it comes to intrusion detection, because again, as I said before, part 2 of the book, or part 3 of the book talks about intrusion detection, where it's actually a system level thing. It's not tied to a particular layer. Okay, like TLS provides security services in transport layer. A VPN, for example, or IPsec provides security services in the network layer, and so on, right? But firewalls usually they provide protection to the entire system, and it's not specifically tied to a particular layer. It can actually combine so many layers together, right? So there are specific techniques that are usually applied not to a specific layer or a specific protocol data unit. If you remember the term protocol data unit, which refers to the unit of information in a specific layer, right? So these types of mechanisms, they are not tied to a particular layer. Like for example, trusted functionality, in which which defines, like for example, policies. These policies could be policies for example, for the password, مثلا. Okay, define certain policies, مثلا. Security label. Security label refers like to a watermark or to like file properties, like for example, whether this file is read-only or something like that. Okay, so these can be part of security as well, but it's not tied to a particular layer. It's tied to how you store information on a server. It's not related to how you transmit the data by any chance. Event detection here talks about the fact that through like some investigation, how can we detect that there is a security breach? Okay, so usually the way to do that is to investigate or to look at security audit trail. Security audit trail is like audit logs that stores all the events that happen in a particular system. Like Amr logged on at this particular time, and he tried to, to authenticate to this particular server by using this method of authentication, and through that he did this. He modified this file, he removed this file, he added this, things like that. Okay, all these actions are stored using the audit trail mechanism. Okay, the audit trail mechanism specifies exactly what to store about each action that the user uses to interact with the system. Okay, through that, the intrusion detection mechanism, or the intrusion detection in general, looks at these audit trails, and then it says, oh, okay, there is an event here. It looks like when Amr logged onto the system, he tried to remove that file to provide like some security breach to a particular service or to a server or something like this. So we alert the system administrator or the security administrator to try to look into that event. So event detection and security recovery. So we could do actually event detection, but without recovery, right? We can detect the security breach, but then we have to manually react to it, right? But we can do automatic recovery. So the system can, in fact, detect and recover from some of these security breaches automatically, right? So that's what we refer to as security recovery, right? So these are just like very high-level idea about some of these mechanisms, but as we said, we will, in fact, dive very deeply into some of these in a lot more details later. So this matrix is actually very important because it shows the relationship between the services and the mechanisms, right? So as we said, usually to provide a particular security service, whether at a certain layer or layer agnostic, we have to group some of these mechanisms. We have to group one or more of these mechanisms. So for example, for authentication, we probably do encipherment sometimes because, again, as we said, because we need the password not to be exposed, things like that. We have to use digital signature to provide origin authentication, so it's this part of authentication. And we have to do authentication exchange. So all these mechanisms have to come into the picture in order to facilitate the peer entity authentication, and so on. So for example, traffic flow confidentiality, we have to do encipherment, we have to do traffic padding, as we said, and we have to do routing control. So in many cases, we group all of these together in order to provide confidentiality or data concealment, right? So the relationship in general is a many-to-many. Okay? So also, as you can see, encipherment is needed in all these services, right? So it's in general many-to-many. So encipherment is needed actually to provide many services, whether it's like layer specific or layer agnostic. واضح كده؟ Any questions? Attack surface is actually it defines a reachable and exploitable vulnerability in a system, and what that means is that, you know, like it's no matter what we do, actually the system will have some attack surfaces, and that's what usually the attackers try to exploit. Like for example, if we provide a service like HTTP, and HTTP usually uses port what? Port 80. Okay. Can we afford, مثلا, in any system or any network to close port 80 completely? As long as it's open, it's an attack surface. It's an attack surface. Okay. It's an exploitable venue that the attacker can, in fact, use to get into the system. Okay. So we cannot close port 80 by any chance. Can we actually say, oh, okay, let's not close the port 80, but we have to close HTTP service, مثلا. We have to disable HTTP service. Okay? Can we do that? Well, maybe yes, maybe no. In some cases, we cannot. Okay? So that's actually sometimes the strategy or the philosophy that some people use to provide security. Some people, they think that security is provided by just closing, you know, doors and windows and everything. So I need to have all my system completely closed to protect it. Okay? But you can never do that. You can never do that. Can actually any service provider do this? He will not provide any service. Providing service to others means that you have to have like some doors and windows open so that they can utilize the service through these doors and windows. And as long as these doors and windows are there, these are what we call attack surfaces. You cannot actually close all of them. You can never close all of them. So the intelligence or the best way is to open services but make it secure. Okay? So for example, HTTP, like if you add S here, so it becomes HTTPS. HTTPS is like secure HTTP, right? And in that case, we can actually use port 443 or other ports. Okay, but the security services or attack services are not just like services and ports. These sometimes are related to codes. So we talked about this, or we talked about this. So open ports, they represent an attack surface. Service available, like HTTP, okay? This is an attack surface. There is code, like for example, if you open the browser, at any page you can say view source, right? You see the JavaScript code. That's an attack surface, okay? So if some people can view that code, you know, they can use it to make any attack on the system. That facilitates some kind of attack to the system, right? Or SQL. These are just, you know, again, scripts, SQL scripts. So sometimes these are, in many cases, these are open. I cannot encrypt SQL script, you know. So these are all exploitable attack surfaces. The biggest attack surface is actually human, right? And that's usually the weakest link, statistically. So sometimes, like we as human, like we tend to make it simple for ourselves by using like simple passwords, simple policies, and that's an attack surface, right? So if somebody uses like trivial password, it makes it easy for the attacker to just guess it, okay? In fact, this is one of the weakest links, because once someone reaches into your password, all security services become useless, because he can impersonate himself into the system as if he's you, and he can do all sorts of damage to the system, right? So these can be categorized as network attack surface, whether it's a port. So we can say that these are network attack surface, okay? Software attack surface like code or SQL. So these are software attack surface, or the human attack surface, which is this one. This is a human attack surface, okay? So these are just examples, and these how you categorize it. Okay, واضح? Any questions? طيب, attack trees. Attack trees defines the concept, the very famous concept of divide and conquer. Attack trees, the attackers use attack trees to say, okay, so let's just have like a very ambitious goal. Attack bank XYZ, okay? So this ambitious goal needs to be divided into, sub goals or sub, tasks or sub steps that you need to do. So you cannot simply say that attack a bank, so let's try to, attack it in one step. Usually you have to take, different steps. So attack trees, tries to define systematically what are the mechanisms or the steps that the attacker can use to perform a certain attack. So attack trees, as you know, like the root is the objective of the attack. So attack bank XYZ. So this is the root of the tree. And then you have branches. These branches, represent like different ways of how you perform that attack, right? And as these branches, they go from one level to another, these are the sequential steps that you need to do in order to perform this attack successfully in a specific branch. So by doing this attack tree, you try to use divide and conquer. So let's do this, let's do that, let's do this. And, hopefully one of them, not hopefully, hopefully not, but one of these branches, if it leads to a terminal node that's performed successfully, this means that, unfortunately, the attack has been successful. So that's like, this is, for example, an attack tree for bank account compromise. So bank account compromise can be done through multiple ways. One of them, this is usually the easiest and the fastest way. If this actually, succeeds, then خلاص, that's it. Because once you compromise the credentials of anyone, this means that you can authenticate to the system as if you are that person, and you can, access his or her account, you can transfer money to yourself, and you can do all sorts of things, right? And as we will see later, all the encryption and all the security services, they come, as an implication of successful authentication. If the successful authentication has happened, all these services become useless. which means that all the keys used for encryption and everything is already known to you. Okay, so we'll study that. So we can do injection of commands to the network. We can do like user credential guessing. This means that, for example, you can use traffic analysis to guess, or you can use exhaustive search, things like that. Assuming that the person has done like some security policy violation and used password 12356 or something like this, then this becomes very easy. Or use of known authenticated session by the attacker, which happens very, very often. A person logs into a bank account and then he leaves the machine and it's gone, right? So that's a very common mistake that some people do. And somebody else comes, he finds that the session is still open. Okay, so let me transfer money to myself, and that's it. Okay. And these are, if you find like a green node, this means like this is a terminal node that refers to a particular step or a particular mechanism that's used in that case. So whether it's a theft of token here, sometimes this is a physical token. Like you're not familiar with this, but in some cases we used to use, especially people who worked in the industry, they used to give us like physical tokens that we have to use to authenticate ourselves to the network, like physical tokens. Sometimes there is a code that randomly is displayed on this token that you have to use in order to authenticate yourself to the system. Okay. So sniffing, man-in-the-middle attack, we will discuss all of these techniques. But this is the concept of attack tree. This means that we divide the big objective into smaller objectives, and then we try to perform systematic steps in order to perform that attack. Security models are also very important concept. In fact, we use system models, especially, you will be used to that as a researcher in general. We use system models in all our papers. So the first thing, in fact, in your project, in your course project, this is usually the first thing that we start with. Network security models or system models in general, they are used to characterize, the functionality of a particular system in a graphical way. Okay, it abstracts the functionality of a particular system in a graphical way. So, for example, this is the model for network security. So here we represent the message by this bounding box, and then this is Alice, or this is the sender. The sender has a message, which usually is like the message is exposed. Then we can use some security-related transformation, whether it's encipherment or traffic padding or anything. Okay, so this representation like abstracts many things, right? So here we convert this message, whether by using encipherment, traffic padding, routing control, or any combination of them. Okay, so all of these are abstracted in this particular part of the system model. We transform that into a secure message. Okay, and this message gets transmitted over a channel. Again, we abstract the channel by representing a pipe. So this channel represents wireless, wired, anything, right? So that's an abstract representation that characterizes a channel, right? And then this secure message gets transferred on the other side, and then we have to use like some, again, security-related technique to transform the message into the format that it was, and then the recipient can receive it. So that's the interaction between the sender and the receiver. There are some intermediate entities, like for example, here we talked about the notarization or the arbitrator or the certificate authority that vets any message coming from a particular sender or going into a particular receiver, and that's used for authenticating the origin and for non-repudiation, so that the sender cannot deny that he or she sent this particular message. So that's what we mean by here the arbitrator. And of course, we have to have the assumption that there is an opponent. Okay, so the assumption that we are transmitting a message or transmitting any information, and this message is not listened to, that's a naive assumption. So we have to have the assumption, as we will see in a minute, we have to have the assumption that the attacker has access to all secure messages, which means that all the encrypted messages are being listened to. Okay, this is the minimum assumption. In fact, in some cases, we have to assume that even the attacker knows some exposed or some plain text. In some cases, that he or she will get access to some plain text. Okay. This model actually is usually applied in transport layer, network layer, things like that, right? Sometimes we have to design our encryption technique using that assumption that the attacker not only knows the encrypted message, but he or she knows actually some of the plain text messages. But hopefully not all of them. That's another security model that models network access. Again, so that's where usually the security, the network security model usually refers to the defining the model for the layer-based interaction or the layer-based security model, where we provide particular service, whether it's confidentiality, integrity, things like that, in a particular layer. So this network security or network access security model usually refers to how to protect a system. So there is an opponent that tries to access. So there is actually an opponent and a legitimate user as well. Try to access a particular system through some access channel, right? So this is the gatekeeper that tries to protect the system from illegitimate access and tries to facilitate only legitimate access to the system. Again, that's not tied to a particular layer usually, or it actually combines multiple layers together. So gatekeeper here is usually a firewall, مثلا. This firewall allows only legitimate access to the system or to the resource behind it. And to do this, gatekeeper or the firewall needs to, again, check the request and verify the validity of that request through multiple things. And sometimes, actually, the firewall has to check different protocol headers in the message itself, not only on a particular layer. Sometimes it has to check the network header, the transport header, the network access header, and so on, before it actually admits the request to the system. And as we said, this model is actually the one that we usually use for denial of service attacks, and that's the trickiest type of attack ever, because imagine if you have millions of these requests coming. Sometimes millions of these requests come per second to the system, okay? And in the middle, you have some legitimate access or legitimate requests. How can you deal with that? So just the fact that you process the illegitimate requests and categorize them and filter only the legitimate requests from all of these is actually a very tricky job, okay? The unwanted access here, we're not going to study this a lot because, again, this refers to the Trojans and viruses and stuff, which is usually used to store or to compromise a particular server or machine, and that's usually part of information security course, not the network security course. So that talks about usually like how to store مثلا code or scripts or something like that, and how to have unwanted access to these types of resources or scripts on a particular server. So we're not going to actually cover this a lot as part of this course. So at the end of this chapter, we talked about some standard bodies. We talked about NIST, or National Institute of Standards and Technology, and these are concerned mainly with standardizing the security mechanisms. So this usually covered in part 1, which we will start in a minute. Okay, so that covers the security mechanism. So until now we are in part 0. And ISOC or IETF, so this NIST, they have what we call FIBS, or the Federal Agency that deals with the measurement science and so on. Federal Information Processing Standards, FIBS. You don't have to memorize all these terms, by the way. And ISOC, they have a, حد فاكر؟ IETF, bravo عليك. So these are the groups that standardize about security services, okay, which is part 2 of that course. So we'll study that starting from chapter 4 and 5, and okay. So for example, TLS, they usually use what we call RFC. Remember the RFC numbers? So RFCs, they refer to some standard specification for network service in a particular layer that describes, for example, TLS or HTTPS or IPsec and stuff and so on. Okay. So that's the summary of this course. So we talked about computer security concepts in general. This is the biggest umbrella. We talked about the network security as part of it, which has to do with securing information while it's being transmitted. We talked about the major security architecture, the difference between passive attacks and active attacks, and the models that we use to describe the different security services, whether it's authentication, access control, and so on. And we talked about the difference between security mechanism and services, and we talked about attack services and the categorization of these. So in probably, I mean, okay. Okay, so starting from chapter 2, we'll start part 1 of the book, which talks about the security mechanisms. So the first chapter here talks about symmetric encryption and message confidentiality. So this is the security model that we're talking about. For symmetric encryption, we have Alice. Alice has like a plain text. Plain text means that it's exposed. It could be like in English language, it could be anything. So this plain text with the definition of a secret key and a specific encryption algorithm, just like مثلا AES, we'll talk about AES and other encryption techniques. So the message gets transformed into a ciphertext. Okay, this ciphertext is a transformation of the message that's supposed to have no correlation with the original message, and this message gets transferred over the channel, as we said. So one of the characteristics, or some of the characteristics that we need to talk about here, is that the security here, or the confidentiality or the concealment, is guaranteed by the secrecy of the key, not the secrecy of the algorithm itself. The algorithm is known to everyone. Okay, and that's why the different the types of attacks for confidentiality, they target guessing the key. That's the only unknown thing. Okay, so they try to guess the key. Okay, so the other thing is that this particular functionality should guarantee reversibility, because we'll talk about other mechanisms which do not guarantee or do not require reversibility. So if Bob, okay, has the same key, and because here we're talking about symmetric encryption. Symmetric means what? The key must be the same, okay, between Alice and Bob. So if Bob has the same key, right, then he must be able to reverse the message and get the original message, okay, using the decryption algorithm. Okay. So there is, of course, something here behind the scene, that in order for Alice and Bob to have the same key, there should be some key exchange or key distribution. So we'll talk about حتى key distribution as a mechanism. How can Alice and Bob maintain or make sure that they have the same secret key? Because this is the only guarantee for message concealment, right? So how can we have both of them have the same key even though they did not communicate anything? So that's also part of the security mechanism that we'll talk about probably in the next chapter. Okay, type. So there are two requirements in the for these encryption or encipherment techniques. So there are two requirements. A strong encryption algorithm, and here strong is a fluffy word. Yani how strong? So how strong? How can we guarantee that this encryption algorithm is actually strong? So we'll talk about this because right now it's a very abstract word. The sender and the receiver, they must obtain copies of that secret key. And that also refers or involves, as we said, key distribution or key exchange mechanism that's not in this picture. Okay? So here the assumption is that they already have the same key, and the encryption algorithm works based on this assumption. The security of the symmetric encryption depends on the secrecy of the key and not the secrecy of the algorithm, because the algorithm is well known to everyone. So why would it be well known to everyone? Okay? Why would the encryption algorithm be known to everyone?
Could be like a challenge. Like I will give you my algorithm and I still challenge you to find like the crypt or to find like a key from this algorithm.
Yeah, but the more يعني critical reason for this is that in a way we kind of have to, because I mean if Alice can talk to Bob, Alice may use a device which is manufactured by a vendor, and Bob could use another device which is manufactured by another vendor. So again, we're talking about the same requirement for a standard to be a standard. So if the encryption algorithm here is known, but on the other side is different, then they cannot talk to each other. They cannot really, even if they have the same key. Okay? So having the encryption algorithm known would mean that this will contribute to the widespread use of this encryption algorithm, right? So as we said, it's kind of challenge that even though it's well known, but it's also strong, right? So that's a challenge, and that's why the NIST sometimes do that. They actually do that through like some calls to developers and to researchers. We need, to have this particular mechanism with this requirement, and then they receive some, proposals from different developers, and then they say, okay, so through the investigation, we find that this particular proposal is the best based on certain, performance measurements, and then they use it as part of the standard. And of course, that person will get rewarded. So knowing the encryption algorithm will contribute to the widespread usage of that particular algorithm. Manufacturers can develop hardware or software services, very fast, right? Because the encryption algorithm is known, and the only unknown thing is the secret key. And these chips can be widely available and incorporated, and that also promotes even small startups to try to develop chips or IPs using these particular algorithms and sell these IPs to big vendors. So, for example, Apple can use a security chip that's provided by a particular small company, right? And they use this chip as part of their devices. And that's in fact what they do. Okay?
Is it feasible for private company or networks they use their algorithm that is not public, for example?
Yeah, but yes, and for example, مثلا, طبعا I don't know exactly, but I wouldn't imagine مثلا the Pentagon, they use مثلا these exposed algorithms to provide communication internally, right? I wouldn't imagine they do that. You could have your own proprietary technique for any of these security services, right? That's not known. But the implication of this is what? You can only use that internally. You cannot use that for external communication, right? If that's what you want, then it's fine. It's fine.
It's fine, but I mean, is it used by?
Yes, as I said, I mean, I don't know for a fact, but I would imagine that many organizations, they actually do that internally, right? Like, for example, مثلا يعني some big مثلا presidents or something like that. So they cannot use the same level of service that we normal people use. So in many cases, they can use proprietary, techniques and devices and things like that.
Communication between the countries sometimes. They
مثلا
agree
or
with them
yeah.
and they
But that usually uses some kind of service like VPN. But again, they can use, as part of this, they can use proprietary protocols. They don't have to use the standard protocols.
But Doctor, there might be like weaknesses in the algorithm, and since it's not well known to everyone, they can't.
صح, that's a challenge. صح, but يعني that's why these algorithms, by the way, how can we ensure the strength of these algorithms? We will not analyze this so much as part of this course, right? Because that requires information theoretic background. But some of these techniques will get deeply into the analysis. So we'll study that. So, for example, for مثلا DES, triple DES, we'll study this in a minute. The strength of these algorithms are usually verified through some information theoretic analysis. Okay, we'll talk about يعني, how we can analyze this in a high level, but not very, very deep, because that requires information theoretic background. But yes, you're right. I mean, there could be some vulnerability in these algorithms, but in many cases, and in fact, in all the mechanisms that we will study as part of the course, there is no weakness in the algorithm itself. The weakness is in the way that we define the length of the key. Because as we will discuss, there is no attack-proof algorithm. None of these mechanisms are attack-proof. But that's not because of the weakness in the algorithm itself. It's because of the limitation of the size of the key, which allows any kind of brute force attack or exhaustive search to try to find the right key at some point. But we will see about how can we make this difficult. But you can never make it impossible, right? Like, for example, we'll talk about all these algorithms. These are breakable in seconds using quantum computers, for example. So quantum has made all these all these techniques invalid, to be honest. But the good news is that, I mean, quantum computers are not really used, at least for the next decade or so. They are not widely used, at least for the next decade or 2 decades, right?
Victor, the algorithm, are there like some specific algorithm for storing data and like hard disk, and some different algorithm if they are transmitted?
Yeah, so the difference here بقى in مثلا the security techniques in general for storing information on a specific server, this may or may not be standardized, because that's usually not used for communication. Okay, so our challenge here, because network security in particular, is that there is some type of communication. Communication means that you need to have a protocol, and protocol means that you need to have like some interoperability between 2 devices or 2 vendors, okay, 2 different vendors, right? But مثلا some organization may in fact use some proprietary policies or techniques to store information on the server, as long as it's stored. But if you need to communicate it, then you have to use some kind of a standard service. Okay, even for security service, you have to use standard service. That's why we have مثلا TLS is a standard, IPsec is a standard, and so on and so forth. Because these are used, again, to transfer information across potentially multiple vendors or multiple manufacturers. Okay, that's the real challenge. And that's why we need to have so many things known. Okay, yeah, for example, last time we talked about the fact that encryption, in many cases, we don't do encryption to what? To headers, right? We cannot encrypt headers. Because again, this message goes through routers, switches, and these switches, they need physical address. These routers, they need IP address. All of these have to be exposed. Okay? All right, so cryptographic techniques, they can be categorized in multiple ways. Okay, one of which is based on the operation or the combination of operations that they do. So some cryptographic techniques, they do what we call substitution. And by substitution here, we mean that we usually divide a message into like blocks. We'll talk about the difference between blocks and streams and stuff like that. So we divide the message into blocks, and then we get this block. We transfer the block into smaller parts, okay? And each part, we use that part to look up a table, okay? There's a table here, and even this table, as we will see, even this table is public. It's well known, right? So we take this part, we look up a table, and then we get the value here, and then we put this value in replacement of this particular part. So this is what we call a substitution. Substitution means that we substitute a value, small part of the message, into another part through, in many ways, through some lookup tables or something like that. Transposition. Transposition is slightly different. Transposition here talks about the fact that, you know, this part can be switched or swapped with another part. So we take the message, and then we do some permutation to the different parts of the message. Okay? And again, the main objective is that the result message will have absolutely, almost zero correlation to the original message. Right? And it has طبعا very high correlation with the key, okay, which is usually, hopefully, is unknown. So this is the difference between substitution and transposition. And of course, the product system talks about involving multiple stages of these, because as you can imagine, encryption does not perform one of these functionalities. It usually performs a combination of all these functionalities in a systematic way to, again, provide the transformation of the message. The encryption techniques also are categorized by the number of keys. So if you have the same key at Alice and Bob, this is what we call symmetric encryption. If we have a public key and private key, if Alice and Bob each will have 2 keys, okay, this is what we call a asymmetric encryption. Okay, an example of symmetric encryption we will study. طبعا لو I will study in a few minutes. DES, triple DES, AES, and all of this. An example of the asymmetric, we'll talk about RSA and elliptic curve and all of this. Okay. So based on the way in which the plain text is processed, and for this we have 2 categories. We have the block cipher and stream cipher. So it's important to understand the difference between these two. So for block cipher, what happens, and again, we have a long message. The message could have any arbitrary size, right? We divide this message into blocks. So block 0, block 1, and so on, okay? So we take each block, 1 block at a time, okay? And then we apply the encryption algorithm. Okay, we get what we call a C0. We take this, we apply the encryption, we get C1 and so on. In some cases, we actually have to take 2 blocks and stuff like that, which is called mode of operation. We'll talk about these modes of operation. They have particular objectives and stuff, which we will talk about. But this is block cipher. So what is the characteristics of this? Again, one thing that you may have to have good understanding for is that these cipher texts, they get transmitted over channel, right? This channel could be wireless, could be wired, right? Depending on the type of the channel, you may have some errors in this cipher text. That's not an attack, okay? It's not necessarily an attack, or it's not attack on integrity or something, right? It's a channel error, normal channel error, okay? specifically if you're using protocol like UDP. Okay? So one of the weaknesses or one of the problems, of course, block ciphers are very strong from a security perspective. Very strong from a security perspective. Why? Because using these blocks, you can easily guarantee that there is no correlation between the ciphertext and the block text. Okay? There is no correlation. If there is high correlation, then you can guess the key easily. That's not, of course, the objective. Okay? So it's always to try to, يعني the main objective, معلش I will get to some probabilities, بس a very, very simple thing يعني. The requirement is that the probability of having a certain value for the key, okay, given that you know a specific ciphertext, okay, given that C equals C0, and given that C equals C1, and given all types of ciphertext, this is actually equal to the probability of K equals to K0. And what that means is that knowing one or infinite number of the ciphertext will not actually help you to try to guess the key. You understand this? Okay? This is an ultimate objective that all the developers of these techniques try to achieve. There's no correlation whatsoever between the ciphertext and the key.
So is that
No
each
correlation.
block was encrypted in a different way? Like each block was encrypted in different
No, that doesn't mean that. That doesn't mean that. The encryption algorithm will encrypt the different blocks, but looking at the ciphertext will not, even if you have infinite number of these ciphertexts, will not enable you to guess the key easily. This means that the only way to guess the key is to do exhaustive search. Okay? As we said, it's not impossible, it's possible. But we'll try to make it as difficult as possible. That's the main thing. Type. Going back to this, okay? So this is the block cipher, and block cipher, that's what it does. So the strength or the pros is that it's very powerful, from a security perspective, okay? For us as network engineers, مثلا, okay, if there is any type of small error here, and in fact you will try this in the assignment, in one of the assignments, okay? If there is any simple problem, even 1 bit, okay, this will cause the fact that you cannot reverse engineer that block, or you will have very high probability of error in that block, which means that block ciphers are not in any way tolerable to natural network errors. Okay? They are very strong from a security perspective, but they are not tolerable to natural network problems or natural channel errors, which might happen in networks, right? Might happen. So in many cases, if the protocol is tolerable to these network errors, it saves us a lot. But unfortunately, these block ciphers, they have issues when it comes to network tolerance. Is there any solution for this? Yes, we'll study that. Okay, type. Is this the only category? No, we have other things. Stream ciphers. Okay, stream ciphers are the other way around. Stream ciphers, they talk about the fact that you have the message. This is the message. We don't divide it into blocks necessarily. What we do is that we have the key, and from the key, what we do is that we use the key to generate what we call a random sequence. And this random sequence could have as many bits as you want. Okay? We'll see how this is done. We generate this random sequence, and then eventually what we do is that we do a very simple operation. We XOR this random sequence with the message. And this is called Vernam cipher. الفيرنم cipher ده is the very primitive يعني it tries to just XOR the key with the random sequence which is generated from the key يعني with the message. Okay, so is this يعني طبعا of course as you can imagine the result here is the ciphertext which is like big ciphertext that corresponds to the original message. And as you can imagine, this ciphertext is very tolerable to network errors in that case, because if you have any error here, okay, the error will be localized in the message, in the constructed message. Why? Because it's just a simple XOR. Can you visualize this? Yeah? Because if it's a simple XOR, okay, if there is any localized error in the ciphertext, when you reconstruct the original message, because reconstructing in the original message is done through what? XORing again, if you have the same key, you have the same random sequence, you XOR this random sequence again with the ciphertext, you get the original message, right? So XORing allows the error to be propagated exactly as is. So it remains localized in the message, which means that one of the very important advantages of stream ciphers is that it's very tolerable to natural network errors. Very tolerable. We'll try this in the assignment. You will have more appreciation. يعني. You'll be able to evaluate that with your own hands. يعني. ماشي? But is it strong from a security perspective? The answer is probably no. But why do we use it? In fact, this Verenum cipher, what it does is that هو the ciphertext equals to the plain text XORed with the key or a function of the key. Okay? So the attacker knows the ciphertext for sure. Okay? If the attacker knows the ciphertext, does that guarantee the strength of that simple encryption technique? The answer is yes. The answer is yes. There is a theoretical mathematical proof that if the attacker knows C0 and C1 and C2 and everything, this particular rule is actually maintained. There is a mathematical proof, right? Which means that from an information theoretic perspective, Verenum cipher is in fact very robust against the attacks where only the ciphertext is known. But is this assumption is good enough? The answer is no. How can the attacker know anything other than the ciphertext? Are you trying to tell me that the attacker may in fact know like some plain text? In fact, in some cases, yes. Or at least part of the plain text. As we said, headers. What else? If two people are communicating, like for example, they are having conversation. They are communicating in Arabic or English or whatever. So most probably when they start, they will say, Assalamu alaikum wa alaikum assalam. خلاص, I listen. And I assume that the start of the communication, they will have the word Assalamu alaikum. مثلا. Okay? When a person tries to start communication with the server, the first thing he or she will send is, in fact, the credentials. So I know one thing about the credentials. I know his username because it's exposed. Everybody knows that. Okay? So that's a plain text or part of the plain text I actually know. So if one plain text is known, what is this?
Key. The function of
The function of the key is what? Is the ciphertext XORed with the plain text. خلاص, I got the random sequence, and from the random sequence, that's why in string ciphers they don't use the key directly. They use a generated random sequence from the key to make it a little bit hard. but knowing the random sequence will allow you to guess the key much faster. Okay, so from a security perspective, stream ciphers are usually not as robust as block ciphers. Okay, but stream ciphers are tolerable to natural network errors much more than the block ciphers. So these are the main characteristics of this. We'll talk about this again and again when we start talking about the encryption mechanisms. Any questions?
Is it related, like, usually you stream with UDP protocols and
No. It has to do with, so many factors. Like, for example, also one of the characteristics, we did not cover it here, is the complexity. Usually, stream ciphers, they are much less complex compared to block ciphers, and we'll see why in a minute. So stream ciphers are fast, are very much to network errors, but they are not very strong from a security perspective. The attack to stream ciphers are usually faster, but because they are simple and they are less complex, in some cases they are used in low power devices, for example, in security protocols when security is not required to be very high, things like that. Okay. In many standards, by the way, sometimes they define, and we'll talk about this in IPsec, for example, they define security levels. Okay, and there are certain techniques and mechanisms for this particular level, and there are different techniques and services or different levels of security for another level, and so on. Okay, so if you wanna have high security level or robust security service, then you have to pay. Nothing is for free. Okay, so this trade-off will revisit that and again. Okay, because as we said, there's no mechanism that's attack-proof 100%. Okay, we always try to make it hard. So how hard? It's always based on trade-off. Okay. So there are, as we said, there are certain assumptions based on which we design our security technique. For example, Vernam cipher, is based on the assumption that the attacker knows only the ciphertext, and it's actually proven to be very, very robust if the attacker only knows the ciphertext. So that's why the minimum assumption is that the attacker has information about the ciphertext, for sure, one or more. Okay, but as we said, the attacker may in fact know some plain text or at least part of it. Okay, and we talked about some scenarios of how can the attacker guess or know some parts of the plain text as well, which he can use to do some traffic analysis and reach to the key much faster. But there is also an interesting assumption, is that not only does the attacker know the ciphertext and or the plain text, the attacker may, or we may have an assumption that the attacker may actually choose the plain text that they can get the ciphertext for. How does this happen? Like if here we have Alice, so the attacker here might in fact might have some level of compromise to Alice in such a way that the attacker may in fact control the plain text that he can give to Alice to produce the ciphertext. Okay? And the difference between this and the other one is that knowing the plain text does not mean that you can control what plain text you can give to Alice, right? You can have certain assumption about a certain plain text, but you cannot control. Here, we assume that the attacker has some compromise, and that should happen through like some man-in-the-middle attack, or maybe I'm inside a server now, and I can in fact control how I can send a message through HTTP to another server from that particular device. So I can in fact send a particular text, okay, and have the this device produce the ciphertext that corresponds to this plain text. Choosing or controlling the plain text allows you to have more control, which will make you actually perform the traffic analysis much faster, as you can imagine, right? I can control what type of text I can have Alice to convert to a ciphertext. So I can arbitrate and I can create some plain text so I can know some information about the key faster. Okay? Same thing happens to Bob. I can also control what ciphertext that I can give to Bob in order to give me the plain text. Same thing, right? So that's called a chosen ciphertext, right? Which means that for Bob, I impersonate myself as Alice. Oh, here is a ciphertext. Please convert it to a plain text, and then somehow I have access to that plain text inside the device that Bob uses. Okay. So by controlling that, I can have actually a combination of both. Chosen text. Chosen text, I can, in fact, control what plain text or what the ciphertext can be converted either by Alice or by Bob. So I can permutate, certain plain text here and certain ciphertext here, which allows me to probe Alice and Bob and to get to the key much, much faster. ماشي؟ واضح? Anything is not clear here. Okay? So, of course, the more assumption the developer would drive to design the security technique, the more robust the outcome of this technique will become, right? So, if I have more assumptions of these, this means that the encryption algorithm will, in fact, be very strong. If I design the security or the encryption algorithm by assuming all these assumptions, I should be able to come up with a very strong technique. So even if the attacker knows some plain text or a ciphertext or even control the plain text or the ciphertext, the security or the encryption technique will still provide some level of security. That's a big challenge. And there is no such thing called attack proof or 100% attack proof. So a cryptanalysis and encryption scheme is computationally secure if the ciphertext generated meets one or both of these following criteria. As we said, it's not 100% proof, but if the cost of breaking the ciphertext, breaking the ciphertext, which means implicitly that we can generate the original message corresponding to this ciphertext, which means implicitly that we have some information about the key. If the cost of breaking the ciphertext exceeds the value of the encrypted message or encrypting the message, that means that I wanna break into a bank account, a certain bank account. Okay, so one of the possible strategies I can use attack tree where so I will get a server that costs $5,000 to try to perform 10 to the power 15 operations in a second, so that I can break and guess the key in an amount of 5 minutes. Okay, so I break the account and then I get to the account and I found only $1,000 inside the account. So which means that it's not efficient, it's not feasible. So the cost that you have spent in order to break into that bank account is much more than what this account has, okay? So in that case, we say that the encryption algorithm has achieved the objective, right? Or the time required to break the cipher exceeds the useful lifetime. Okay, so I will. So instead of buying a server of $5,000, I will buy a server of only $1,000 because there is like $100,000 in the account. Okay, so it seems to be economically feasible, right? But this $1,000 server will have to spend a week, okay? And unfortunately, the security protocol that's used as part of the bank, has to recycle these keys after 5 days. So whatever I have done is actually useless, right? And in fact, all the security protocols that we'll talk about, they have to have limited life cycle for these keys. Okay, these keys have to be renewed every now and then, right? So either the cost is very high or the time required is higher than the lifetime of the key. In both cases, the encryption algorithm has achieved the objective because, you know, if I have unlimited and I don't change the keys, and you know I have unlimited amount of dollars in the account, then unfortunately the attacker will spend a year, will spend 2 years, and eventually he or she will guess the key and will break that. And that's why, you know, all the security services that we'll learn as part of this course, they have to have like some way of renewing these keys every now and then. In fact, on the level of minutes in some cases. Every few minutes we have to renew these keys. Or every certain events that happen in the system, which is affected sometimes by different factors like mobility, disconnection, things like that. Okay? So an example of a trivial or easy one is like the Caesar cipher. I'm not sure, maybe many of you have been introduced to the Caesar. Caesar cipher was one of the first algorithms that was ever, you know, invented. That it's based on a specific number for the key. Like for example, the key is 6 simply, and 6 means that you know the message the message itself is encoded using the alphabets, the normal alphabets. So it actually uses some kind of transposition based on the lookup table, which is the alphabet. So everybody knows the alphabet, and if you have A here and the key is 6, this means that A will be shifted in the alphabet. So instead of putting A here, I put a مثلا I, which is 6 positions from A. It's very, very simple technique. Yani. This was one of the first that probably has used during the Roman Empire or something like this. ماشي? It uses simply transposition. So as we said, brute force attacks, they use exhaustive search. What is the complexity of brute force attacks? If it mainly depends on what? The attack is mainly depend on what? Key size, right? So if the key is K, assume like K is like, let's say مثلا 56, like this, uses a key of 56, right? How many operations do I need to guess the key? Worst case. 2 to the power 56, bravo عليك. Yes, 2 to the power 56, right? This is the worst case. But on average, we usually need half. Why? Because we assume that the key is a random variable. Okay? So a key is in fact a random variable which starts from the size, يعني starts from this to this, and the value, يعني I'm talking about the value اللي هي from 0 to 2.56. It can get any value out of these, right? What is the probability of taking any of these values? Assume this is the worst case. Assume it's uniform, right? Assume it's uniform. Okay? This is the worst case, but in fact it's not uniform, right? So if it's uniform, what is the average of this? Huh? What is the average of this? 2 power 55, which is half, يعني. Half, which is 2 to the power 55. So on average, I need this amount, right? On average, I need this amount. In fact, 2 to the power 56 is the worst case. But on average, in fact, I need to just guess half of these numbers. And I will probably get the value of the key with high probability. يعني get the value of the key. Get the value of the key. How can I verify that I reach the value of the key?
I know the plain text or
لا, you don't know. You don't have to know the plain text itself. You know that the plain text مثلا is English. So if you reach to a readable English language, this means that this is in fact a valid plain text, which means I have reached the key. Yeah, something like that. Again, that requires certain assumption. So on average, I need half. Of course, as you can imagine, the key distribution, the probability distribution of the key values is not in fact uniform, which means that it has certain probability distribution. And that's why, in fact, in practice, the attackers, they need fewer, and sometimes, this is the bad news, they need less number of trials, even less than half in many cases, to guess the key. And that's bad news for us. So unless بقى كمان if there is like known plain text كمان, okay, so that also helps to try to reduce the number of guesses. So the worst case, brute force, and on average we need half the key value or the maximum key value, right, which is 2 to the power the key size, minus 1, this is half, right? But if the attacker knows plain text, that will reduce the number of trials even more. So to supplement the brute force analysis, we use other information, and that's what we call traffic analysis. Traffic analysis. So we can use, I don't want to put ideas in your head, but you can use machine learning to get as many properties as possible. So if for example, I have fixed, ciphertext size, and I have certain plain text that I know, and I have all these, certain plain text that I know, and I have many ciphertext, and I have this and that. I take this in machine learning, and then I try to guess the key, and I have certain مثلا probability distribution that I know. I don't have to know the key values, but I can, in fact, have some information about its probability distribution. That's a property. I get all these properties, and then I can use some attack technique using machine learning, whatever, to try to reduce the number of guesses to the key. Okay? So this is an example of brute force. So if I have, this ciphertext, for example, I have a certain ciphertext, I apply different arbitration of, or different permutation of the key value, and I get some text which is not readable, right? But when I look at it, it looks like number 3 is somewhat readable. So it looks like the key could be actually 3, something like that. Okay, so that's an example of how brute force actually works. So I have to have some assumptions about the message itself. In some cases, مثلا for network messages, I'm expecting to have certain مثلا values for particular headers. Okay? So if I have certain values in the particular headers, even if the message encoding itself is not in English, then if I have these values in the headers, that indicates that most probably I have reached to the right message. In that case, I can get the guessed key, and I can use that key. Okay? If I use the key on multiple future messages and I get, similar values for that header, this means that, I'm reaching to the right key. We are teaching you how to break the communication. All right, so talking about a specific symmetric key encryption techniques, one of the major building blocks or major ingredients that NIST came up with is what we call fizzle structure. The fizzle structure defines certain product operations or certain transposition and substitution operations on a plain text to get into the ciphertext. Okay, and as you can see, it looks complex, but in fact it's simple, and that's one of the strengths of this fizzle structure. So what happens is that using certain K1, K2, K16, and so on, we perform 16 rounds starting from the plain text all the way to the ciphertext. So this plain text usually is 64 bits, and it's fixed. So what happens for if the message is larger than 64? This is we divide it into blocks such that each block is 64. So what happens if the last block is not 64? We use padding, but in that case, padding is for alignment, not for security. ماشي كده؟ طيب, so we divide that plain text into left element and right element. So that each of them is like 32 bits. Okay, so so if you look visually, in fact, we can simply say that right element of I at any round, at any stage, any of these stages, right element of I is in fact the function. This is called the round function, okay? The round function applies to right element of I minus 1 together with ki, okay? This is XOR with left element of I minus 1, okay? So this simple logical equation describes this part, right? And what is left element of I? It's in fact right element of I minus 1. So these simple two equations, in fact, characterizes all these, complicated graph. Okay? That's part of the strength of this Fizzo structure. This Fizzo structure is proven to be very robust from a security perspective. How can people break it? People break these types of algorithms because of what? Because of the limited key length, not because of the fact that this algorithm is really weak in any cases, right? طب how can we prove that this is indeed, or the transformed message has absolutely no correlation with the original message? Again, we're trying to say that the probability of guessing the key, knowing some ciphertext, is actually the probability of guessing the key, which means that if you know infinite number of these ciphertexts, you will not be able to guess the key easily, right? So in order to prove this, okay, we have to get into very deep information theoretic proofs. We will not, luckily, we will not get into that as part of the course, but it's enough to say that it's indeed verifiable, and NIST, in fact, they actually verified that this is from a security perspective and from information theoretic perspective, it's indeed very strong. ماشي؟ طيب, one of the really good things about this is that it can be, if I give you these two equations, okay? In fact, I can have an assignment about this. If I give you these two equations and ask you to program, okay, this in software, do you think it's easy? I think it's doable, right? It's very easy, and that's one of the strengths of this Fizzo structure. It looks complicated, but it's very easy to understand, right? And that, in fact, contributed to the widespread use of the Fizzo structure. Okay, we'll talk about the motivation, why people have deprecated this, and they tried not because of the fact that the Fizzo structure is bad at all. This is because of, again, the limited key length, because here the key is assumed to be 56, of length 56. 56, which means that on average we need 2 to the power 55 operations. Usually, using a simple device like this, it's 8 core, I can perform these operations in 1 hour using this simple device, right? So nowadays, this is becoming easy to do. Okay, let alone بقى talking about quantum computers. ماشي. So this is the decryption side. So this is the encryption side. This is the decryption side. For the decryption side, we perform the same operations but in reverse direction. Okay, reversibility is one of the requirements for any encryption. Like we may have, and that has some implications we'll talk about. We may have the strongest encryption algorithm, and for that we're trying to really make the correlation 0. But then if we need to reverse it, we can't, even if we have the key. So what is the use of this? So reversibility is one of the very important requirements for encryption algorithm. Okay? Because again, reversibility may not be a condition for other things. We'll talk about that. I showed you K1, K2, all the way to K16. Okay? So where did this come from? All of these keys are, again, some permutation of one key. Okay? So we get the original key. We go. This is the characteristics of the fizzle structure. So this fizzle cipher design elements has certain characteristics which is based on block size. Of course, if I increase, as we said, block size is usually 64. We'll talk about DES. DES uses 64. So if we use a larger block size, okay, what is the implication of this on that particular structure? Well, the structure will be more complicated, right? And that will add some complexity, right? But in terms of security properties, we will probably have stronger security, right? Again, because larger block and there's no correlation whatsoever between them. So trying to guess the key, because larger block will mean essentially that also the key is larger, which means that, again, to break it, you need more time and so on. The key size is also a very important parameter in that case. The larger the key, again, the larger the complexity, or the more the complexity, and the larger the time required to break into that. The number of rounds. In order to appreciate this, that's why we have مثلا I will switch context شوية اللي هو deep learning. Why people have tried to use deep learning? Because the more depth we have in these layers, the more analysis we can do, the more knowledge we have about the information. Here we can have the more rounds, which means more and more permutations, which means that again we reduce the correlation to the original message more and more, right? So the more rounds we have, the more we can reach to no correlation between the ciphertext and the original message. But what is the cost? Again, more complexity. So it's always a trade-off between complexity and security strength. Okay, sub-key generation algorithm. One thing we didn't talk about, I told you that we have symmetric key, which means that we have one key, okay? But here, the key itself, and then we perform certain permutation, we create 16 keys, and then we call them sub-keys, okay? So from one key, we can generate 16 keys or 16 sub-keys, and then we use these sub-keys for the different rounds, right? So also sub-key generation also is a factor that affects the complexity and the security. The simplest مثلا key, as you can imagine, is circular shift مثلا. I can get a key and I can perform certain circular shift to create multiple keys out of this key. And that's a very simple way of creating sub-keys. Assuming that the key itself is unknown, so the sub-keys are unknown, so I can do that. But as we will see in a minute, they do more than this, usually. The round function itself, one thing to pay attention to here is that when NIST tried to define the physical structure, they did not specify the round function, a specific round function. And they did not even specify any specific sub-key generator. Okay, they said that this is left to the developer. So during their mathematical analysis to try to prove that this physics structure is indeed strong, they used an abstract definition for the function, and they have used no particular subkey generation. Okay. The fast software encryption and decryption. This, in fact, in many cases, the encryption is embedded in applications utilizing software. And as we said, just because of the fact that we can characterize the physics structure using these simple two equations allows us to create whatever software or hardware to really develop this physics structure very fast. And that's one of the strengths of this physics structure, really. And the ease of analysis, of course, which, only two equations. If I perform them in a recursive way, I have done the physics structure. So it's like it's the same block, but it's repeated multiple times. And every time you do that, you get into more and more less correlation of to the original message. And that's one of the good properties of this, right? So I can give these two equations to information theoretic, scientists. Okay, so they can work on analysis using information theory to try to prove the strength of this. I can give these two equations to software developers. They can start writing the implementation of this physics structure using software, using chip design, using something like that, very easily. Okay, and knowing the fact that this is known, this is public. Okay, but still has some good characteristics. So with that, the NIST, they define the physics structure, but so far they did not specify any complete encryption technique, right? Physics structure is like, it remains a structure, but they did not specify any round function. They did not specify any subkey generation. So I need to have a complete mechanism.
And the number of rounds is also up to the developer?
The number of rounds in the physics structure, they specified the 16. And that must have to do with the analysis that they have done. They have to provide proofs based on specific number of rounds. And as we will see, the first symmetric encryption technique, the DIS, it used the same number of rounds to guarantee that they follow the same mathematical analysis that has been done to prove the physics structure. In fact, it leveraged the physics structure as is, almost as is.
So 16 is at least, it's like at least 16 rounds?
No, it's exact. Yes. In all the security mechanisms that have been used as part of NIST, other than AES, because AES is totally different category, we'll talk about that, they have used 16. Why? Because if I use more than 16, you're right. I should have more, robust technique. I'm increasing the complexity. So, the assumption is, I can have more security robustness. But why 16? Because 16, in fact, achieves a good trade-off, between complexity and security. So, if you increase more than 16, it looks like, or it seems, that the amount of correlation that you will get as a benefit is not there. So above 16, the correlation between the ciphertext and the original message stays almost the same. So you are increasing the complexity without gaining anything. So why bother, right? So 16 is like an arbitrary number. Of course, it's not, exactly clear for us why 16 and not 17 and not 18 and so on. But for them, this actually achieves the trade-off between complexity and security. So why add complexity if I don't, gain some benefit out of it? Okay, which is usually for us as researchers, we usually for a curve, مثلا, when we study the performance given certain parameter, we say that, you know, as long as we are increasing like this linearly, this means that from round to round we are gaining, right? But in some cases, we start to get like some saturation. So I'm paying a cost on the complexity, but I'm not gaining anything in the performance, okay? So here, I break and say, no, this is the optimal parameter. Okay, there is no point of increasing the rounds even more if I'm not getting any benefit, right? واضح كده? Any questions? تمام. So the first thing that we'll talk about is, or the first algorithm, is DES, or data encryption standard. So for data encryption standard, or DES, this is most widely used. Of course, this is not applicable anymore. يعني, because, well, actually, NEST later on, they have deprecated this. They have recommended not to use it. But is this deprecation led to the fact that DES completely disappeared? No. And we'll see some security services that still, until today, they still use this. And we'll know why in a minute. Okay, so DES has been issued in 1977. Of course, many of you have not even born during that time, as part of the FIBS 46, right? So the algorithm itself is referred to as the data encryption algorithm, DEA or whatever. All right, so this algorithm, it uses the block size is fixed, and the key size is fixed. The block size is 64, and the key size is 56. Okay, so the key size is 56, which means that, you know, we need 2 to the power 55 operations to break the key at most, or يعني on average. And that's using nowadays, you know, devices. We can do that in an hour. We'll see that, which is one of the main reasons that NEST has actually deprecated DES from being used. The structure is, or DES uses very, very minor variations. In particular, they define a specific round function bar, and they define a specific subkey generation. We'll see that. Okay, so they add to that, because we have to specify a certain round function in order to have an end-to-end functionality. Yani. Okay, and again, the strength of this has like two concerns. The algorithm itself, and in many cases, the algorithm itself is not weak, because there is a proof that the correlation performing the round, these rounds systematically like this, the correlation is indeed very low, but it's dependent on the key size. So in many cases, the strength of that algorithm depends on the key size. Okay. So the use of the key is the biggest problem. And why 56? Why not more? Why مثلا the developers in NEST مثلا, why didn't they use مثلا 500? Okay, because of the complexity, right? One of the main characteristics of this, as we will see here, is in fact the bit manipulation or the bit level operations. Okay, as we will see, the bit level operation makes the algorithm itself really hardware friendly, but not very software friendly. The implementation is easy, but the cost of implementing this in software and the complexity in software is really high. For starters, we don't have like a programmatic variable called bit, right? What is the minimum parameter in programs? It's actually unsigned int or byte, صح? But software naturally is not very efficient in dealing with bit operations. It can be done, but it's slow, very slow. That's one of the main reasons that all these bit-oriented algorithms, they have full short to AES after this, because AES used non-bit, oriented manipulation, as we will see. So anyway, so all what we have done in this is that they have, here, as we can see here, this is in fact exactly the fuzzy structure. It's exactly the fuzzy structure. Okay? So what they added is in fact initial permutation and inverse initial permutation. Okay? And when it comes to permutation, this means that we take the bits and then we do some transposition to these bits. We move this bit here, we move this bit here, we swap bits and so on. So that's the initial permutation and that's the inverse initial permutation. Okay? Do we have to memorize this? No. We don't have to memorize this. ماشي? You need to understand the structure of the fizzle, structure? Yes, you need to understand the structure. You need to understand the characteristics of it, of course. But you don't need to memorize these permutations in details at all, okay? When it comes to permutation, by the way, there are three types of permutations we will talk about. There is, straightforward permutations, which means that the length of these bits is the same like these bits. So it's a straightforward permutation. There is permutation with contraction, which means that the size shrinks. And there is permutation with expansion. Okay? Each one of these, again, they have some properties and some characteristics, some slight characteristics. Okay? We'll talk about them from a high-level perspective. But anyway, as we can see, this is the fuzzy structure. This added the initial permutation and the inverse initial permutation, which are, normal systematic permutations, right? And they have also specified, this is what, the subkey generation. Okay? So they have added initial permutation, inverse permutation, and they have specified some subkey generator. Subkey generator is based on taking the key. This key is 56. صح? In fact, this particular key is padded to become 64. Okay? And this key is used through like some permutation, and there is permutation choice 1, and there is circular shift. Circular shift is easy, صح? We know the circular shift, right? Circular shift, we get like some bits and we circulate it. That's it. Very easy. And there is a permutation choice 2. This permutation choice 1 will, in fact, reduce that size to 48, sorry. Okay? Which means that it's a permutation with contraction. Okay? Permutation with contraction. And then we do the circular shift, and then we do another permutation with contraction. This is 32. One of the important characteristics of permutation with contraction is that in many cases, it's irreversible. واضحة دي? It's irreversible. Which makes sense. As permutation with contraction, يعني, we get 2 bits and we transpose it to become 1 bit. From 1 bit, can you easily get the 2 bits? In many cases, you can. صح? For permutation with contraction, sometimes, or in many cases, breaks the reversibility. In many cases, it breaks the reversibility. طيب, هو أصلاً, يعني, are we required from K1 to get to the key? No, there is no such thing. صح? So we're fine. And that's why they use the permutation of contraction here, because there is no requirement for reversibility. So that's one thing to pay attention to. So of course, this K1, as we have seen from the physics structure, it goes to the round function. صح? We'll see now how the round function looks like. And then we perform these rounds as we have talked about before. That's it. Okay? So we'll see. This is a bit wrong. So this is actually 48, sorry. So this is 48, not 32. The permuted choice 1 is done once at the beginning. The permuted choice 2 is done at every single round. واضح كده? Okay? So the circular shift is also applied at every single round. ماشي؟ طيب. We'll zoom in. So this is actually these are the rounds, the different rounds, and this is the round function. So the round function, yeah, so here, yeah, actually this, so we'll see that now. So here, we take the ciphertext. When we perform, one thing to pay attention to is that permuted choice 1 is done once at the beginning, not at every round, صح? Here. So the Ki gets XORed with something as part of the block that we have. So as we said, we have the left element 32 bits and the right element 32 bits. So for each layer, we get the right element, and this is the round function. The round function is based on 3 simple operations. One of them is permutation with expansion. The permutation with expansion, okay, preserves the reversibility. Preserves the reversibility, okay? And then we XOR this with Ki. This is the permutation with expansion. So from a certain size, we get a bigger size, which means that a bit might be permuted to multiple bits, to 2 bits or 3 bits or something like that. Okay? So we can perform this in a reverse direction easily. Okay, we can do that. So from 32 we get 48. We XOR 48 with 48, so that's normal. And then we do a substitution with contraction. So what happens here is that we get every 6 bits, and from a lookup table, we use the 6 bits to get into 4 bits and then put the value here. So from 48, we reach to 32. And here it's not permutation. This is a substitution. If it's permutation with contraction, that might violate irreversibility. But they didn't do that. I'm telling you why they have used this as a substitution and not permutation with contraction, to preserve irreversibility. Okay? Hal, from the 4 bits, can I get the 6 bits? Yes, using a lookup table. From the 4 bits, I can get the 6 bits using lookup. As long as I have the lookup table, I can get to the 6 bits. I can do the reverse operation. ماشي? So with the help of the lookup table, I can get to the 6 bits again, which means that I can reverse this operation easily. And that's why they didn't do the permutation with contraction, okay, to preserve reversibility. And then I do straightforward permutation, okay? Someone might ask, why do we have the permutation here? Okay, why do we have the permutation here? For in some cases, there is no straightforward. Why do we have 16 rounds? نفس الشيء يعني. Why do we have 16 rounds and not 17 rounds? It's the same thing. We're trying to reduce, the objective is trying to reduce the correlation more and more. And this particular structure, it seems to achieve that position. The more permutation, the more levels of permutation we have, the less correlation we can achieve compared to the original message, right? ماشي? But there are certain operations that have يعني clear reason ماشي. But in some cases these particular permutations and the way that's structured can be proven empirically or can be proven mathematically, okay? But for us we have to stick to whatever we have been defined in the standard. Any question so far? We'll stop here because it's لا بس we'll cover this عشان بس يبقى complete. Okay. So this actually described, it's not new. This actually described how we can estimate the cost, okay, as a function of the key size. As we said, if we have a key of size 56 and we use the DES مثلا, so the number of alternative keys is actually 2 to the power 56. So these are all the alternatives that we have. But if we assume that we have uniform distribution to the key, on average we can get to half of this. So half is almost the time required. But if we assume certain number of operations per second, we can spend 1 hour to break this using any of the very widely common. In fact, nowadays it's even less. So that's one actually weakness because of the fact that DES talks about bit manipulation. Okay, it's not software friendly, and that's why in many cases they prefer to use hardware chips. But hardware chips makes it really rigid in terms of it's not easy to reconfigure or make it flexible in terms of changing the parameters and stuff like that. يعني if it's software, I can easily, مثلا change the size of the key, do this software. But if it's hardware, it's not easy, صح? The good thing about AES, مثلا, for example, is that it can use different sizes of key without really doing much changes in the algorithm itself. So it's tolerable to the key size more than this. But the only way to change this is to use triple this. Why did they use triple this and not change the algorithm completely? Because on one hand, it's done in hardware, and this hardware is widely used in millions of devices that people use. Okay, so one thing we could do easily is to say triple this is nothing but 3 chips. And instead of using 1 chip, we use 3 chips, which means that instead of doing 16 rounds, we do in fact 16 and then 16 and then 16. And for each one, we use even different key. So 168 is in fact 56 divided or times 3. Okay? So by doing this, we have made the cost or the time required all this number of years. Okay? So that's a good way of trying to mitigate the weakness, not of the algorithm, but the weakness that's embedded into this by using limited size key. Okay? But AES itself is very much software friendly, as we will see, because it's based on matrix multiplication. We know how to do that in software. Very efficient, right? So it's, in fact, we can change the key easily in software. And that's why we have a number of keys that can work very efficiently with AES. We'll talk about AES next time. Okay? Any questions? Okay, so we'll stop here. We'll talk about